So hello for those just joining us. I do apologize. We started this resonance structure already. My fault. Hannah was supposed to tell me to record and she didn't. So, so with this molecule, we've got 1, 2, 3, 4 resonance structures in all. And as we were saying, it's common to see that when there's a negative charge, as a new pi bond forms, it normally means an adjacent pi bond has to pop. So we keep the same number of pi bonds and lone pairs each time. Occasionally there'll be exceptions to that, but it is a good general guideline. Each resonance structure will have the same number of pi bonds and lone pairs. As we're saying, we'll look later at chemical reactions which have resonance structures, and the resonance structures will point to the relatively reactive points in the molecule. So if this molecule was to undergo an addition reaction, you can see why this point in the molecule could be reactive, because it's got electrons to use and make a new bond. We can see why this point could be argued as reactive, because there's carbon anion nature, a negative charge to this carbon, which could instigate some chemistry. Also, of course, here. And then finally, the oxygen itself has an electron-enriched environment over the course of those resonance structures. And that's many of the reactions we'll do this semester will be about these nucleophiles and electrophiles. Nucleophile just meaning nucleus lover, an atom somewhere in a molecule which normally has a negative charge. So it's allowing us to instigate a new chemical bond if it has too many electrons. And it normally reacts with something which we call an electrophile, something which loves electrons, loves to receive electrons, and they tend to be parts of the molecule. I hate it when it joins up the lines. Parts of the molecule which have positive charge, those that have electrons and those that need electrons. So figuring out where the charges go around the molecule as we look at the resonance structures can allude to the relative points of reactivity and where a molecule becomes substituted. Any questions about that one? So molecules which need resonance structures drawn, which begin with some part of the molecule containing a negative charge, that's a hot spot. That's where things will start. And it's usually this ebb and flow of a new bond forming as we turn the lone pair into a bonding pair like this, but also a bonding pair turning into a lone pair. So we keep that same number of lone pairs and bonding pairs each time. Okay, boom. Let's take a look at the next one. And work on this one together. So this time we've got a hot spot at the end of the, get out, why are you there? At the end of the molecule with a carbon which is electron deficient, positively charged, and so it's hungry for electrons from its neighbors that can help out with that. So if I draw it quickly again, so a positively charged carbon, it needs electrons, it wants to borrow electrons, and so, of course, its neighbor, this carbon here, has access to these pi electrons, so it swings the electrons around, and we, from this position here, we just rotate that pi bond around to plug in that electron deficiency. So as we draw the second resonance structure, that's the only change in the molecule, the position of the pi bond. And so with this bond pulls away from this carbon, that becomes the carbon with the positive charge. Remember, the arrows are showing how the electrons move. I've seen from past semesters people getting confused and using arrows to show where the charge finishes up. That's just a consequence of the movement of the electrons. But it's the electrons which are moving, and that's what you're showing moving. And the charges as they hop around is a consequence of suddenly having more electrons and being negative, or having less electrons and being positive. So now at this point, this poor carbon has an atomic orbital which is empty. There's the bond to the hydrogen as well, which I'll draw to the side so you can see it. So it has an incomplete octet and only controls 1, 2, 3 of the 6 electrons around it. That's what's making the carbon positively charged, now that it no longer has a slice of those pi electrons. So this is a new hotspot, a new problem point in the molecule. And so this is the carbon it needs rescuing from its positive charge. It can turn to its neighbor, and so its neighbor rotates that bond around. So we show where the electrons are coming from. It's coming from the bond, and they're finishing up as a new chemical bond. If it finished as a lone pair on the carbon atom, then we point to the carbon. But we're pointing to where the new location for this pi bond will be. So positive charge now appears there. And it's very regular in its appearance, the charge popping 1, 2 carbons down the line, charge popping 1, 2 carbons down the line. So the movement of that charge is fairly consistent in how far it hops each time. So our next development, because now this is the hot spot, the electron-hungry carbon. So it needs help from its neighbor. So this pi bond swings around to form a next resonance structure. Look how consistent it is. Wherever the charge is, it's an adjacent pi bond that swings around, an adjacent pi bond that swings around. And so now this is a carbon with the trouble. It looks to its neighbor, which has access to pi electrons. And so it will help out. And that bond swings around to give us our last resonance structure. Now this is a new resonance structure compared to the first one. It is new because notice that the single bonds and double bonds are in the opposite locations, like we saw with the original example of benzene and the 2 resonance structures that we had for it. So although we've got the positive charge on the same carbon, the pi bond positions has rotated. Okay. Is it safe to erase this one, or do we need another minute? No complaints, so I guess we're okay. You can always do a screen grab on your computer and then paste it into a PaintShop Pro thing or something. You want to keep it, or just freeze the video later on. Okay, so disappearing, 3, 2, 1. Let's see. 2 more. I think these are the last 2 that we're going to do in this chapter. Oh, a couple more. 1 more on that page, and then we're acid base, yes. So let's do this next one together, and then I'll let you loose for maybe 5 minutes to do this one, and then one on the next page. Okay, positive charge there. That's a little bit trickier, this one, because of the lone pair that, of course, is on the nitrogen atom, making up its octet. So there is a lone pair there, and that will come into play and show us one of the exceptions with resonance structures when it comes to the number of lone pairs and pi bonds. Let's start with this. Oh, a 7-membered ring, that's always a bit trickier to draw. Did I go too far? Yeah, kind of. That's not too bad. And positive charge there. Okay. So again, that charge showing us a hot spot where things are going to start happening. And it's a carbon atom which doesn't have enough electrons. It looks to its neighbors. It's a neighbor on the left which can help because it has access to this pi bond. And so the pi bond swings around to fill in that electron deficiency. Just for completeness, put the lone pair in. That charge is moved over there. So the hot spot here now, this is the carbon which is electron hungry. So it looks to its neighbor to help it out. It says, yeah, I've got these pi electrons. Enjoy, or something like that. And we get a third resonance structure. Oh, that didn't go to black. There's a third one. And we might suspect that maybe this is the end of it because we have run out of pi bonds and neighboring atoms. But the unhybridized atomic orbital of the nitrogen does have that lone pair of electrons. And the carbon says, I'm not fussy, I'll take those. And so we turn that lone pair into a bonding pair, a pi bond, to plug in the gap. So we actually see an example where we have changed the number of pi bonds and lone pairs. That's a positive charge on the nitrogen. So pi bonds or lone pairs can come to the rescue of that positively charged atom. Any questions about those ones so far? We're starting to feel a bit better about drawing resonance structures. Very quiet. Oh, thumbs up, thank you. And I think there's a question of the day video on resonance structures that I've got to do later on this afternoon. And if people want more examples, I can certainly do more examples. And look at the back of the Gazinski, not the Gazinski-Smith, that's the general chemistry. Look at the back of the McMurray chapter 2. You'll see extra examples there. Give them a try. Write them on a piece of paper, take a picture of it, text it to me, and I'll tell you if you've made any mistakes with them. Okay, about to clear this one off. Right, so I will check with my daughter, see what she is up to. She's been very quiet.
Very quiet. Real quick on the for the tests, how will we be evaluated on our ability to draw resonance structures? Will we be taking kind of like paper tests, or will all our tests be electronic?
It'll be paper tests. You'll have just an exam paper like those old exam papers you see on Desire to Learn, and just fill in the blanks and complete it. So I don't worry too much about artistic talent because mine's isn't that great either. So for example, if you're trying to draw a benzene ring like this, and it comes out like I might make a little bit of fun of you. I'm kidding. I mean, as long as it's got all the atoms in the right places, then that's fine. Bit of practice. Most people are pretty good at drawing benzene rings, to be fair. The one that usually gives most people trouble is the 7-membered ones. I'm used to drawing them because my PhD thesis was based on a compound called Tropolon. And Tropolon looks like
How do you spell that? It sounded like trouble.
Tropolon.
Oh.
Yeah, I've got that structure burned into my brain for all time. I'll probably put it on my gravestone. This was the basis of my PhD. Basically, you've got the ability for chelating to a metal here. If you use some acid, use some base rather, and strip off the proton, you can make a chelate, a metal complex, from the Greek chelate for a claw, because it looks like the molecule is making a claw around the metal. And we would have substitution on the back end, and so we could make these big, long, rod-like molecules. And so these molecules, rod-like molecules, could be stacked together neatly to make liquid crystal phases. And that was my PhD for 3 years back in Hull, back in from 1995 to 1998, trying to make liquid crystals. It was a lot of fun, made some very good friends. Okay. Oh, I was back in Hull there. I haven't thought about that. Oh dear. I haven't thought about that in a long time. Okay. Take a look. Is that the next one? Or have we done this one? Oh, this is the next one. So give this one a try. There's our hotspot. And this has now got too many electrons. So it's looking to offload. I can tell you it's not in this direction, because this carbon, this normal carbon, of course, is just sp3 hybridized, which means it doesn't have any atomic orbitals to load electrons onto. So you're going that direction around the molecule. See how many resonance structures you can draw and I'll come back in 5 minutes. Also, if you get finished, think about the one on the next page. For these two molecules, one of them is more stable than the other. Through resonance, could you make an argument for one being more stable than the other? Let's see, where was it? Okay. Let's give it, we'll make it 10 minutes. That gives you time to finish and also maybe grab a drink or something. And then we'll check our answers. And then we can look a little bit at acid-base chemistry. So we'll be pretty much finished the chapter, if not completely. My daughter has been very naughty today. She has not gotten a Twizzler today. What did she do? She wasn't eating her breakfast, and then she started taking food and just dropping it on the floor to make it look like she'd eaten her breakfast. Takes after her mother, obviously. And then what else? Then she had a big tantrum about a piece of paper that she wanted to keep, and she dropped it in the bathroom sink, and it was all wet. As well, it'll dry out. No, it won't. Yes, it will. I'm a scientist. I know these things. But she wasn't having it. Yeah, you know, taking 202 before 201 is tricky. It's a big leap. There's lots of little things which you haven't had practice with to make things relatively easy. And then it just takes time. But as soon as you feel you're having problems, come and talk to me about those problems. If you tell me about your problems, I can help you solve them. Sitting alone in silence is not the way. I don't want anybody to feel that they're suffering. There's enough suffering in chemistry as it is without people keeping their problems to themselves. I was lucky. Chemistry was just one of those things I really loved doing and also happened to be very good at. So in my senior year, I'd been the top student for 2 years running, and we had a class of about, I want to say about 120 taking chemistry at that point in junior and senior year. And most of the people taking chemistry in my year at that time were young ladies, about, I don't know, 80%, 90% female in the class. And because I was the best student, I always was getting lots of attention. It felt great. I'd never had attention from women like that before in my life, before or since. Everybody wanted to know me because I'd tell them their chemistry answers. And I still remember to this day, one time I was sitting in the library, finishing lunch. You could eat lunch in the library in those days back in Glasgow. And one of the really pretty girls in the class, Jocelyn, asked me for help with a problem. And I'm doing the problem, showing her and looking at it, and then I look and suddenly there's this line of young ladies, about 7 or 8 deep, waiting to ask me problems in chemistry. This was quite a religious experience for me because women have never lined up for my attention before. It's like, oh. Oh, that was a highlight, and then the rest of my life went like that. Right, let's see what my daughter is up to. What is going on? Chem is try. Oh, I'm going to steal that one. I need to put that on my office wall or something. My daughter appears to be content watching Peppa Pig. Actually, she loves watching the things I watch. She's very much a daddy's girl. So there's, I don't know if you guys have seen this, various YouTube sites I follow. There's this guy called Nuke's Top 5. He does ghost videos every week. And so my daughter likes to watch ghost videos with me. All right. If you're looking for something to watch late one night, try Nuke's Top 5. He's one of the better ones. It's never videos which, that's obviously fake. That's somebody just jumping up and down. They're usually pretty good quality, the ones he picks. If you like that kind of thing. Well, my daughter watches Peppa Pig. How did we find Peppa Pig? I'm pretty sure, that's a British kids cartoon. I usually try them on most of the British kids cartoons. But it's weird. My son especially, he'll be obsessed with a cartoon for maybe 3 months and then he'll never watch it again. We had a Dinosaur King phase, and then there was a Pokemon phase, and then what was it? Megatron, Ultron, what was it? What are they called? I forget. Whatever those mechanoid things are. And now, because he likes playing Minecraft, he's obsessed with Minecraft videos. Okay, guess we're ready to get back to it. Let's check, did I switch off recording or did it just stay on? Nope, we were still recording, so we're fine. All right, let's look at this one, another 7-membered ring. That's the ones that give people problem trying to draw normally. So the initial structure with a double bond there. Lone pair creating the negative charge there. So there's too many electrons on this carbon, as you can see with that lone pair. It's trying to offload some electrons. All atoms would like to be neutral. They don't like carrying that positive or negative charge. So offloads electrons to its neighbor, because its neighbor already has an octet, so a new pi bond would be trouble. So that existing pi bond has to pop and the electrons retreat back to the far end of that bond, away from where the electrons are. And so we get a resonance structure. Be careful where your arrows start and finish. It's a lone pair on the carbon, so the bonds or the arrow should start from the atom and it finishes where the electrons are going to finish up. Remember, these arrows are showing the movement of the electrons themselves. So it only starts on the atom. If it was a lone pair on the atom, it only starts between the atoms if it's a bond which is on the move. So let's see. So we've got a double bond there now, a lone pair of electrons there, and of course the carbon to oxygen double bond there. This is our new hotspot, a new point of trouble. We can take it a step further because the neighboring carbon still has access to pi electrons. And so this bond comes in, and the existing bond pops out to the far end. Oops, I missed out a bond there that time. So that negative charge finishes up on the oxygen atom. And that's as far as we can take it. If we put those electrons back in, then this bond has to pop, but it again retreats back to where we were before. We can't extend and utilize this pi bond here. It's not part of the flow of electrons. So this was just bogus or non-essential. It's not part of the chain sequence, so to speak, that we built up. So just 3 resonance structures for that one. Okay. Everybody ready for this one to be erased? See if I did erase it and someone needed it. Can I bring it back? Oh, I can. Okay. So do yell at me. You can shout at me and tell me I've gotten rid of something too quickly and I can bring it back. That's a good thing. So for these two, which one would you imagine to be the more stable structure? Resonance has a huge deal, or is a huge deal when it comes to stability of molecules and intermediates. So let's see what we can draw in terms of resonance structures. So we take this first one on the left, and just because I like doing it, I'll redraw again. Positive charge there. That's the bit that's unhappy. It wants to draw in electrons. And of course, the neighboring carbon here does have access to electrons, and so we can draw a resonance structure for it. I'll draw it straight down, so we're keeping this side clear. So there's a resonance structure that looks like that. However, with our second molecule here that looks very similar, there's a pi bond in there. This is the atom which has trouble, which is electron hungry, but its carbon neighbor is not involved in that pi bond. It's its carbon neighbor which is involved in the pi bond. But this guy doesn't have lone pairs like a nitrogen and isn't part of a pi bond. So there is no help coming to the rescue and no resonance structures. So our first molecule, because of that resonance, is considered a more stable intermediate molecule. The more resonance structures you can draw, the greater the stability, because that positive charge is a weakness in the molecule. And the more resonance structures you can draw, passing that charge around, like with friends passing a heavy burden around, that helps stabilize things. So the more resonance structures, the more friends you have to help carry the burden, the better. Okay. So now we can finish up with some acid-base chemistry, which is hopefully just another refresher. Look out for a video later today as well. I will think today about what we want to do for next Wednesday for lab. Whether we're going to try and do the lab we missed last week, or maybe try and do 2 labs. I'll have a think and look at how tricky it's going to be to try and do 2 at once. I don't want us to be overwhelmed, especially on that first day in lab. So we might keep to this, well, I don't know. We'll see. We shall see, okay? Right, so, but I will make an announcement before the start of the weekend so everybody knows what we're intending to do next Wednesday. I might just keep that little acid-based lab anyway. Oh, I remember what I was going to do. Yeah, we might do, yeah, we'll do, I think, that first one, but we might try and make a start on one of the next labs which has individual tests. The biggest problem usually with doing a lab, hey baby, that's my cat in case you can't see what's going on here. My baby. Well, actually, she's not a baby anymore. She is 16 years old. She is a very old kitty. Still sprightly. Still catches mice and just spits them out on my chest when I'm asleep in the morning. Anyway, that was too much information, wasn't it? So, yeah, we'll do that very first lab we intended to do, and we'll try and sneak a little bit extra of one of the next labs. Most of the time when we do lab, it's an experiment with maybe 2 hours of heating or refluxing, and so that's difficult to stop. But there's a couple of labs coming up where you're just doing little tests which take 5 minutes, go on to the next one. So we're going to try and claw back the time, but we'll certainly focus on the acid-base one because it's a nice easy one to start with and makes for a nice easy first lab report. Okay, on to the acid-base chemistry. So the Bronsted-Lowry definition for an acid-base reaction tells us that the acid is a proton provider, like hydrochloric acid or sulfuric acid, and a base is a proton acceptor, like sodium hydroxide or barium hydroxide. And usually we're talking about Bronsted-Lowry reactions in terms of a proton transfer. And there are a great many examples where that proton transfer to the base causes the production of water and then a leftover salt product. So the acid gives away a proton because a hydrogen atom, if it's lost its electron, all you've got left in the atom is that proton in the nucleus. So we sometimes refer to these hydrogen ions as protons. So it donates a proton, that allows us to form water, and then the leftover bits come together. So the chlorine with the sodium form our second product, sodium chloride. The sulfate with the barium form our last and second product, barium sulfate. So a proton transfer is the gist of the acid-base reaction according to the Bronsted-Lowry theory. Whoops. But most acid-base reactions are reversible. And so although we're looking at a reaction primarily from left to right, and it's involving the transfer of a proton, there's also a reaction from right to left, with that proton, like a tennis ball in a game of tennis, being batted back and forth. That proton is just swung all the way back to the original molecule. And so we've got 2 competing acid-base reactions. We can split up the chemicals into what we call conjugate pairs. 2 chemicals whose formula only differs by the presence or absence of the proton. Conjugate pair, two chemicals which only differ by the presence or absence of the proton. And with each conjugate pair, we can look at the original chemical, and if it's about to give away the proton, of course it's acting like an acid. You always think, what is this chemical about to do for it to turn into its conjugate partner? And we find that with conjugate pairs, one of the conjugate is going to be an acid and one of the conjugate is going to be a base, because it's reaching out using a lone pair, reaching out to pick up that proton, retake it to reform the original acid. And chemicals that pick up protons are bases, according to the Bronsted-Lowry definition. It's the same with the other conjugate pair. One of them is an acid, in this case the hydronium ions, giving away that proton to the acetate conjugate base, giving away the proton, so it's the acid, and its conjugate is the one that picks up the proton in the forward reaction. So it's quite often to see these two conjugate pairs with reversible acid-base reaction systems. And the position of equilibrium is always going to favor one of the two reactions. In this case, we can see with the longer arrow, the back reaction is favored. So this is considered to be a relatively strong base and strong acid. And these two chemicals are relatively weak acids and weak bases, because they're not very good at transferring the proton back and forth. Likewise with the second one here. Again, for that reversible system, we can break it up into these two reactions with conjugate pairs across each of the reactions. The NH3, so for its conjugate, we're looking for a chemical that either has one extra proton or one proton less. Certainly if it's NH3, can't be anything about oxygen because it's not in the original formula. It's just a number of protons, hydrogens that change. So its conjugate partner has to be NH4, because it's about to, in the forward reaction, pick up this proton. So this is the base. Well, its conjugate partner gives that proton away to the hydroxide. The arrows here, kind of like the resonance arrows we've been looking at, the arrows are showing where the electrons come from when a new chemical bond is made, and also where the electrons go in a bond when a chemical bond is broken. That nitrogen to hydrogen bond breaks. Nitrogen is more electronegative. It takes the electrons when the bond breaks, and so it gets rid of its formal charge. Every conjugate pair has an acid and a base. And with the position of equilibrium favoring the back reaction again, as you can see, we're swimming from right to left mainly. This must be the strong acid and the strong base, and this is the weak acid and the weak base. They're swimming from left to right against the current. This is the weaker reaction. If we look at another example, nitric acid with ammonia. Okay, let me get my pen working. So I always try and use red for the flow of electrons. There we go. So the acid is the proton donator. There is the proton. And it's the base which is going to accept that proton using that lone pair of electrons on the nitrogen. And so this lone pair becomes a bond between the nitrogen and the hydrogen. Because hydrogens are in the first row of the table, they can only have a duet like helium. So if a new bond is forming, the existing bond has to break and the electrons retreat back to the more electronegative oxygen. When a bond breaks, it's always the more electronegative atom which picks up the electrons when the bond breaks, because it has a much stronger attraction for those electrons. So the conjugate form of NH3, as we saw across the page, that would be NH4. With that new nitrogen to hydrogen bond in place. That bonding pair formerly being the lone pair. And then for the acid, giving away that proton, it is its own conjugate produced, the nitrate ion, once that proton has gone. So we ask what the NH4 is. As we look at what it turns into in the back reaction, it's about to give away a proton, so it's acting as an acid. That makes sense because a conjugate pair is made up of an acid and a base. And therefore, that nitrate, to turn into its own conjugate, is about to pick up a proton, so it's acting as a base. We can show that reverse reaction as well. The oxygen, negatively charged of course, uses a lone pair to snatch back that hydrogen, and we go back to where we were. So hopefully that's just mostly just a little bit of a refresher, because I'm sure you did acid-base chemistry with Mr. Mackenzie before. Now we can work out the equilibrium constant for an acid-base reaction. We take this generic one here, just a generic HA formula for an acid, dissolved into water, it produces hydronium ions, and then we've got the conjugate of the acid, it's anion. For the equilibrium expression, that would be products divided by reactants. And because we have aqueous conditions, we of course ignore water in the equilibrium expression. Oh, let's clean up the page. So as we solve for the presence of water, incorporate it into the equilibrium constant, we now have what we call the Ka, the acid ionization constant. Just a fancy term for the equilibrium constant for an acid in water when we realize that the concentration of water doesn't change. And so we can measure the negative log of the acid ionization constant, what we call the pKa. It just gives us a much easier value to work with instead of these really small values of 10 to the minus 4 or 10 to the minus 5. We take the negative log, that's the reciprocal of the number, and so we get nice rounded numbers, normally between 1 and 24. The smaller the value, the stronger the acid. That's all we need to remember about these pKa's, the negative log of the Ka. The stronger the acid is when the value gets smaller. Another quick example of that proton transfer. First one, this is acetic acid. Let's see, use red again. And so it's good at giving away protons because it's an acid. Water is amphiprotic, it can act as an acid or a base. In this case, acting as a base because it's going to pick up a proton from this acid using a lone pair. That lone pair picks up the hydrogen. The electrons in the bond retreat back to the oxygen, and so we produce the conjugate pair. Conjugate of the acid, which will be a base, with a negative charge, and the conjugate of water having picked up a proton, the hydronium ions. We can show some stability of that conjugate that's formed through resonance. There's our hot spot, the negatively charged oxygen. And so with a pi bond next door, those electrons, or one of the electron pairs, can swing in, and we pop those electrons out to the oxygen, and we produce a resonance structure. Just squeeze it in here, down at the bottom. Same number of pi bonds, same number of lone pairs. Oops, just missing my oxygen here. Okay. Next one. Phenol, which is acidic and can interact with water. So again, the water acting as a base, picking off that proton. Very easy target. Oxygen to hydrogen bond because it's a polar covalent bond. Polarized bonds are weak bonds. So the oxygen picks up the hydrogen, electrons in the bond retreat back to the oxygen, and we form that conjugate species, or that conjugate species of the acid. And of course, hydronium ions once more. That phenoxide ion, which is formed, is a conjugate base to the phenol. And we can also show the resonance forms for it to show how stable it is. Quite a few, actually. So that's our hot spot with the negative charge. Electrons are offloaded to the neighboring carbon. And as that happens, the nearby bond has to pop as well. Otherwise, we'd be breaking the octet rule. So those electrons pop back to the adjacent carbon, retreating to the far end of the bond. Again, as we said earlier, when one new bond appears, an old bond or an existing bond tends to pop. And we can perform the same trick several times over. That lone pair swings in next door, and those electrons swing out, getting out of the way. Same trick again. How are we doing for time? Almost out. that'll probably be the last thing we do. Electrons swing in, electrons swing out. And we get our last resonance structure, 1, 2, 3, 4, 5. It is different from the first one, as we pointed out before, because the double and single bonds are in the alternate position. Okay, safe to erase that one off. Let me just see what we've got left to do in this chapter. One more there, and then we get into Lewis, acid and base definition with a couple of extra examples, and that's it. Not much at all. But we are officially out of time. So it'll take us about 20 minutes, I think, to maybe finish this off in person. Yay! Next week in class. So come ready with chapter 3, which is the alkanes chapter, and we'll get started on that next week. Okay. And again, probably before tomorrow lunchtime, I'll put up what our final plan is for Wednesday next week. It will have the very first lab that we're supposed to do because it is fairly quick, and I'll check and see which experiment is the best to make a start on next week as well. Okay, any questions before we finish? So good progress, almost completely finished those first 2 chapters, which is nice. And assuming there isn't some kind of flood next week, or a meteor doesn't land on Johnny Logan, I'll see everybody 2 o'clock Tuesday in G123. So start thinking about the homework which I've got. As I said, I think last night in a video or in an email or something, I felt bad about not having tidied up the homework assignments before now. And it did sound like maybe some people had started to try that first homework. So I just left it as is. So if you did start it, you can continue with that. Now has the 2020 date on, and all the other homeworks have been removed from the other chapters. So as they appear, you'll know that they are true and new homeworks. So polling questions by Tuesday night, homework handed in person on Wednesday, and then we'll have the exam for chapters 1 and 2 on Thursday. Take a look at the practice exams. There are some practice exams, and they'll give you an idea of the kinds of questions you'll see, pretty similar to what we've been doing this past week and a half. Okay. Right. Bye, guys. Take care. Stay safe.